I want to present you today a new solution for an old problem that first was presented at the IOM 1988 and was considered at that time as the hardest problem ever. And most of the candidates to the IOM failed solving the problem. Even Terry Tao, who was only 13 at that time and got the gold medal. This problem, for this reason, became very famous. Some call this problem the legend of question 6, and many mathematicians trained gifted candidates to the IOM using this problem in their training sessions.
Have you heard of the legend of question 6?
Oh yeah, it's a famous question, yes.
Now the questions can be called the legend. However, this right here is the one.
They're given 6 hours to solve question 6. Well, guess what? They couldn't solve it. You didn't get it right.
No, I did not get it right.
How do you feel about that?
Well, you know, you win some, you lose some. Oh boy.
Can we make some comments on these efforts to find a solution to this problem? The statement of the problem is very simple, yet the solutions that were found for most of them difficult to understand. This adds to the feeling that the problem was really difficult to solve. In the mathematics of numbers, we know many problems whose statements are very simple and known as true, and yet so difficult to solve, if unsolvable. Fermat conjecture, for example, Goldbach conjecture. These problems, when they are solved, are using very highly complicated, sophisticated mathematics. Fermat conjecture, which had been solved by Andrew Wiles, needed about 200 pages to be demonstrated. But still, one can always wonder if any simpler or more straightforward solution exists. Fermat declared that he had found a solution to this conjecture, but he could not have used the solution found by Andrew Wiles, as at the time of Fermat, the mathematical concepts needed to find the solution had not yet been developed. So a more simple solution using mathematical knowledge available at the time of Fermat is still open. The beauty of the solution to a problem is its clarity. The fact that it is using mathematical knowledge, and also the fact that anyone reading a solution finds it very clear and understandable, even if it did not find the solution to the problem. We can make a comparison with a chess game. Some very strong chess player will win a game with time-consuming effort, with no spectacular moves, which for some spectators makes things that chess is boring. As some other strong player will find a way to win a game with very clever and spectacular moves, which would give him a prize of beauty, as these prizes existed in the earlier age. We think there is also a beauty to be found in the solution of a problem in mathematics, and this is what I will be trying to find for the solution of this problem. Many solutions of this problem are using the Vieta jumping technique or the infinite descent technique. I must say that as an undergraduate student, I had never heard about these techniques. Therefore, I want to solve this problem using mathematics that are simple and known from any undergraduate student. So coming back to the problem, I think that the initial statement of the problem is too simple. Let us complicate it. The initial statement of the problem was a squared plus b squared over ab plus 1 equal n. A and b being integers and n being integer. And the purpose of the problem was to demonstrate that n squared is equal to the square of an integer for any a and b positive. Why limit the search of the solution and proving only that it is the square of an integer? I would add a few more questions, and the answer to these questions would highlight the full dimension of this problem. Why a and b should be positive and not negative. How can we demonstrate that the expression is true for any integer a? This is not obvious at first sight, as the function is of the type f a b equal n equal n squared. as an example, we know the relation of Pythagorean triples, which is very similar, which is f a b equals c squared. Yet Pythagorean triples have the following solutions. For a equal 1, there is no triple. A equal 2, no triple. A equals 3, you have 3, 4, and 5 triples. A equal 4, no triple, and so forth. So not any A can give the possibility of finding Pythagorean triples. Can we calculate the relation between A and B, which makes this expression work, and prove n equal n squared? The fourth question would be, given an integer n, can we calculate the couples A and B satisfying the fraction? And how many couples are there? Let us go now for the demonstration of the complete solution of this problem. What can we say about this expression? There must be a relationship between A and B, which we don't know, that will satisfy this expression. So let us, for example, say B equal K A. We don't know K, but we can calculate, if we know K, we can calculate A and B. So then this expression, if we substitute B by Ka, we get A squared plus K squared A squared over A squared K plus 1 equal n. And this can be written A squared times 1 plus K squared over A squared K plus 1 equal n. N is an integer if this expression 1 plus K squared A squared K plus 1 is a rational number. A rational number means either an integer or fractional number. Let's call this expression P, and n is an integer if P is a rational number, which means either P is an integer or a fractional number whose divisor is a divisor of A squared. Let us find for which value of K P is a rational number. Therefore, we can write this expression like K squared minus A squared P K minus P equals 0. And the solution of this quadratic equation is K equal A squared P plus or minus square root of A squared P to the square minus 4 times 1 minus P divided by 2. The expression under the radical can be written as a difference of two squares. A squared P squared minus 4 times 1 minus P equal A squared P plus 2 square root of 1 minus P multiplied by R squared P minus 2 multiplied by square root of 1 minus P. And we see from this expression that P is a value that cannot be larger than 1. This means because if it is larger than 1, the number under the radical would be negative. And we are only talking about real numbers. So P is less than 1. And also P is positive. From the definition, as we can see here, n is positive, A squared is positive, so P must be positive. So P is greater than 0, which means that 0 less than P less than 1. We can see that for the value of P equal 1, we get the value of k equal a square. And from this expression here, we can write a square multiplied by p is equal to n. We can see that the maximum value of p being 1, it means that a square is the lowest value of a giving the number n. So if we replace p by 1, we get immediately a square equal n. Once you know a square equal n, you can calculate b equal k a is then equal to k is then equal to a to the cube, because k equal a square. And so you have the complete answer to this first question. First, you demonstrate that the number n is an integer which is the square of an integer, and also you can calculate the number b as a function of the number a, which is b equal a cube. So this is the first part of the demonstration. We could demonstrate that the number n is the square of an integer, and we could calculate, given a, the value of b and of n. We have also proven that a is the smallest possible value, which means that it is not the only value possible. P can take any value between 0 and 1. As a conclusion, the solution shows that to calculate n, we do not even need to calculate the function. All we need to know is a. This is very remarkable and most uncommon. The solutions to this problem can be obtained for any integer a, which is one of the questions asked at the beginning. So there is an infinite number of solutions, each solution using any given integer a. And also the solution of this problem are valid whether a positive or a negative. In the Excel chart, we calculated the function for each a and b value as calculated by the solution to this problem, and found that n and n square answers the question of the problem whether a or b be positive or negative. Now, my final question is, the solution takes just a few lines and less than 2 minutes to demonstrate. As the solution is very simple, can we still claim that the problem was so hard to solve? Now we can go and work on the solution of the last question. The last question being, given an integer n, can we calculate all the couples a, b, satisfying the fraction? And how many couples are they? We have so far demonstrated that for any value of a, there is a solution allowing to calculate b, which will permit to calculate n, and proves that n is the square of an integer. As explained in the demonstration, if we define the value of n, a is the smallest integer allowing to calculate n, which means that for any integer smaller than a, there is no solution to give n if n is specified. So for a given n, we can calculate a couple AB, which is the smallest value we can find. But we have not demonstrated that this AB couple is unique. This is what we will find out now. From the fraction a squared plus b squared over ab plus 1 equal n, we can calculate b from the quadratic expression, which is b equal na plus or minus square root of na to the square minus 4 a square minus n over 2. How can we make the calculations? We start, let's say, first with n equal 1, and we see immediately one answer is a equal 1 and b equal 1. And there is no integer for this particular case greater than 1 which can satisfy this relation. Now let us choose another value, like for example n equal 3 to the square, which means equal 9. If we replace in this expression the value of a being 3 and n being 9, we get b equal 27 plus or minus 27 to the square minus 4 minus 9 over 2, which gives b equal 27. And we can say that 3 and 27 are the start of the AB couple for n equal 9 from the calculations that we made before. Let us now demonstrate that for any given n equal 9, it exists an infinity of couples AB satisfying the fraction. Now we calculate a C as a function of B, replacing A by B in this expression. So we get NB plus or minus square root of NB square minus 4B square minus N divided by 2. If we replace N by 9 and B by 27, we get C equal 243 plus or minus square root of 243 to the square minus 4 multiplied by 27 to the square minus 9 divided by 2, which gives a value of C equal 240. So we can already state that we started with first couple A0, B0 is equal to 3 and 27. The second couple A1, B1 is equal to 27 and 240. And if we continue the calculations the same way, we will get A3, B3 equal 240, 2133, and A3, B3 equal 2133, 18,957, and so on and so on. And this will allow us to calculate all the couple A and B, which satisfies the fraction when n is equal to 9. We found out that the couple A and B are the couples of a sequence U and V, whose terms can be calculated with no need to calculate this expression. You can deduct from the sequence the next couple from the previous couples, which makes calculations much easier. We can state that these couples are the terms of a sequence which we call UV, starting from U0, V0 equals 3, 27, U1, V1 equals 27, 240, which we calculated before, where U1 is equal to V0, U1 equal V0, and V1 is equal to V0 multiplied by 9 minus U0. U2, V2 is equal to 140, 2033, where U2 is equal to V1, U2 equal to V1, and you see U2 equal to 240, V1 equal to 240, and V2 is equal to V1 multiplied by 9 minus V0. Next term, U3, V3 equal 2133, 18,957, where U3 is equal to V2, U3 equal V2, and V3 equal V2 multiplied by 9 minus V1. We can easily find the next term, U4, V4, from the previous terms, U3, V3, U2, V2, which gives these numbers, where U4 is equal to V3, U4 equal V3, and V4 is equal to V3 multiplied by 9 minus V2. So we see that the sequence has a general term which is following: UNVN equal Vn minus 1 and Vn minus 1 multiplied by 9 minus Vn minus 2. Therefore, it's very easy to calculate any couple A and B from the expression a squared plus b squared over ab plus 1 equal n for any given n without need to calculate the fraction. You can just use this sequence and calculate step by step each term from the following terms that have been calculated before. Now to give some examples showing how we can calculate the couples A and B from a general term of the sequence without going through the calculations of the initial fraction. We can, for example, state n equal 4, and we calculate the first term of the sequence, which is 2 to 8, the second term, which is 8 to 30, the third, which is 30 to 112, the fourth, which is 112, 418, etc. As a last example, we can take, for example, n equal to 16, and we get the initial couple, which is 4 and 64, which is actually a and a to the cube. The second term will be 64 and 1020. The third term, 1020, 16,256, etc. So we see that once you know this sequence, you can easily calculate all the couples satisfying the initial fraction given a number A. As a conclusion, it is possible for a given number n, which is the square of an integer, to calculate simply the beginning of the sequence A and B in such a way as a squared equal n and b equal a to the cube. Starting from this first couple, then we can calculate all the couples A and B satisfying the relationship. Now we can make a summary of this demonstration. This demonstration can be fitted in one page for both problems, which is to calculate, to demonstrate that n is the square of an integer, and also how to calculate all the couples A and B satisfying the expressions for a given A. As you can see from these demonstrations, that no difficult mathematics was involved in order to prove these results. It is quite possible for an undergraduate to find such a solution with the mathematical knowledge that he has. Thank you for watching. If you have any comment or question, you can drop a comment below and I will be glad to answer.